Right, so this is just to wrap up the Devil's Fence cross-section that we were building along this line. So we've done the practical, we've recognized all the features, and we were really starting building the section. And remember, we start from youngest to oldest. So some of you may have started putting the faults, so the faults are quite steep, the topography barely affects them. You've got that fault which is quite steep. We've got that fault is the termination of the fault, so I will not be upset if you don't represent it. We've got the granite intrusion that is going through the wall succession, and I think the point that Florian made in terms of the scale at which the wiggles are happening here is related to what we can see on the map. So you can see that, for example, you will have some sort of blobs that happen on the scale of maybe half a kilometer to half a kilometer, and on top of this large blobs that you can see that you have additional small scale indentations that are more on the scale of maybe less than 100 meter, maybe 100 meter on the scale of 100 meters. So you can try to represent that when you put your contact. Then you start building your section from the youngest to the oldest in terms of the beds, and the first bed that you're going to put is this MMC limestone here. The only problem we have here is that it's very hard to constrain the thickness based on what we have along the line of section, because we don't see the top of that limestone. So you will see that for the thickness of most of these units, it will be very straightforward. You've got the deep and deep direction. You draw your beds. The beds are quite thin, and just by drawing the contact between the top, between each of the beds, you will see that the thickness will automatically emerge. But when it comes to MMC, it would be good to have a minimum of knowledge of how thick it can get. So we can use trigonometry to constrain that. So what we need to find is a place where we've got the top and the bottom of the bed. And we find that here, for example, you can see you've got MMC, you've got PMA, which is above it, which is youngest, and we've got ML here, which is older. So that's the bottom, that's the top. These two beds have nearly the same color, but they are not the same. So based on that, what we need to find is a place where we've got deep and deep direction that are relatively homogeneous, relatively constant over the area. So let's imagine that we are in that situation, and for example, we would have deep at an angle alpha in that direction. So what we will do is draw a cross section parallel to the deep direction. So it's very important to have that, because that's the deep angle is the value we're going to use to constrain our thickness. And then you can see that along your line of section, you're going to have a couple of points, A and B, A being the bottom of the bed and B being the top. So this is a map view. So we are here looking at that from above. So what does it look like in cross section? Well, let's imagine first that the topography is completely horizontal. So what we will have is B here, A here, and the bed is dipping towards the west in that case. So we will have something like that. Can try to draw that a bit better. Something like that. And what we want to know is the thickness here, that we're going to call T. And you can see that in that case, this is the angle alpha. And it's very simple, because the thickness is going to be the distance AB multiplied by the sinus of the angle alpha. Right? So that is straightforward. The AB distance is the distance you measure on the map between these 2 points here. So that's that distance here. So remember, that's going to be in millimeters, so you will have to convert that into meters to be able to calculate the thickness in meters that you can then represent on your cross-section. Now what happens is that very often the landscape is not completely flat and we have some topography. So what happens if, for example, we have the point B is at a higher elevation than point A. So in that case, it makes the trigonometry a bit more complicated, but it's certainly not impossible. So let's say that we have a situation like that. B is here, A is here, and we've got that bed dipping at that angle alpha. So alpha being here, the distance with the horizontal. Right, so what we have here is a series of triangles. So if we draw a vertical line here, we have our true thickness here in that triangle. So alpha is going to appear here as well. And we're going to call that line V. V is the vertical distance. And you can see that the thickness in that triangle is going to be the vertical distance multiplied by the cosine of the dip angle. Okay? So how can we calculate V? Well, we've got a couple, just need to look at a couple of triangles more. So we've got another triangle here. And what we have, so V is that distance that we're going to call D, for example, is that distance plus that distance, and that distance is just the difference in elevation between A and B. Okay, so that distance here is that distance, is the difference in elevation between A and B. And this is something that you can get from the map. If you've got your point A, your point B, let's imagine that A is at 6,600 feet, B is at 700 feet. So we have this distance that I'm going to call delta Z. In that case, will be 400 feet. So again, remember to convert the feet into meters to be able to make your calculations correctly. So that's the difference in elevation in feet. And D here, in that triangle, D is AB, so that horizontal distance AB, tangent alpha. Okay, so AB again is the horizontal distance between these 2 points on the map. You will get that in millimeter, convert that into meters. Delta Z is the difference in elevation that you may get in that you will get from the topography. Make sure it's in meters as well. And here we've got all the elements to make our calculation, because if we replace V by D plus delta Z and D by that, we end up with the thickness equals AB tangent alpha plus delta Z multiplied by cosine alpha. Okay, so you should be able to do that. Things to keep in mind: make sure that your line is along the dip direction. Make sure that you have a place where the dip direction and the dip angle don't vary much, because if here you've got, for example, 18 degrees and here you've got 50 degrees, that suggests that there's folding, and it's going to make our calculation incorrect. And in that case, I think there's a couple of places where you could do that. Here, for example, we've got 20 degrees towards the west, 24, so you could use 22, an average value of 22 here, or you've got 18 here, 17 here, so somewhere in this area would work. So that equation is this. So at the end of your handout, you have something that explains how to make these calculations in different situations, whether the beds are dipping inside the slope, are dipping at the same direction than the slope, whether you've got complex slopes. So don't hesitate to make use of that. The formula that they have is slightly different, just because they made conversion in the sense that tangent multiplied by cosine equals sine, but otherwise it's correct as well. So don't hesitate to make use of this resource. And if, for example, you calculate that MMC cannot be is 1,000 meter thick, then on your cross section you know that it cannot appear more than 1,000 meter thick. So that's how you make your section a bit more correct. So thank you for your attention.